Okay, I'm recording. So let's turn this on.
Hello,
Hello, hello, hello.
Cool.
Cool. I'm going to turn this one off so I'm not going twice.
Okay. I think if you still hear me?
Yes.
Okay. So, topic 5. So first things first, we got to talk about homolytic and heterolytic. So what does hetero mean?
Where the bond splits and each atom gets one electron.
You are correct.
Creates radicals.
Yep. So hetero means different. Okay. Hetero means different, which means it's the breaking of two different bonds, right? And lytic just means breaking. So two different bonds are breaking. This usually occurs with a halogen, right? So how the arrows work, it's one full-headed arrow towards the leaving group, because the leaving group is going to be electrophilic, not nucleophilic, right? This will lead to a positive A and a negative B, or vice versa. If you want to do the opposite, you can do a negative A and a positive B, depending on which way you put the arrows. But it's pretty much the same thing, right? And since we both have a positive negative charge, are those ions or radicals?
Radicals, because it's heterolytic.
Nope, ions. A positive charge cation and an anion. So cation, anion, which means it's ions. Homolytic is radicals.
Dang it, that's right.
So homolytic means same. So when we break this bond apart, each one gets half of the electron. So we get A with a little electron and B with a little electron.
That's right. And that creates the radical.
That creates radicals. So radicals are interesting because they will always form and make more radicals. You guys have questions, just ask. Okay. But that's how you do speed number 1. So be very cautious with your arrows. If you don't do your arrows correctly, it's going to be a big, big, big issue. Because you remember heterolytic means movement of 2 electrons, while homo is the movement of 1/2 electrons. They each are the same. Yep. Now, yes, what's up? Homolytic bond breaking usually occurs between molecules that are the same. An example of this would be nitrogen right here, right? Nitrogen are both going to form a homolytic bond. The reason like nitrogen and chlorine, nitrogen and carbon could form homolytic bonds with each other is because they're so close to each other periodic table, they pretty much have the exact same electron negativity, right? Does that make sense? However, carbon and fluorine or carbon and bromine are far enough apart where they don't. And the halogens are so much more electronegative that they can pull both electrons with them, not just half. Can I move on or are you good? Athena?
Good.
Okay. Okay. So this right here is just a energy profile diagram, right? So energy profile diagram should be pretty makes sense. You guys should learn this from 115, 113. We start off with E. A reaction occurs, we get G. Another reaction occurs, we get J. Another reaction occurs, we get L. How many humps do I have? I have 1, 2, 3 humps. How many steps? There are 3 humps, there are 3 steps. How many intermediates do I have? How many intermediates do I have? I have 2. J would be an intermediate, G and J would be intermediates. Well, E is our initial product, our initial reactant, and L is our initial product, our last product. Good. So which one is going to the fastest step?
H.
Nope. So the fastest step, right, is going to be the one with the lowest energy. it's going to happen more rapidly. Correct? Does that make sense? It's faster because it takes less activation energy or less energy to do the hump. Does that make sense or no? Okay. So L, so we start off at E. Is L below or above E? So it takes less energy to make L than it would to make E. Correct? So I am losing energy. That is an example of exothermic reactions. We go back to Chem 2, right? With delta G, Gibbs free energy, right? We want exothermic reactions because exothermic reactions are going to be spontaneous, right? Spontaneous reactions are going to be the best things to have. So going from E to L is spontaneous, which means L will be our fastest step, right? And then what would be the slowest then? Which one has the highest energy? If L has the lowest, which one has the highest? Which one's above E? No, J. That's not the transition state. So we're talking about the products. Yeah. Now we're talking about transition states, which is the humps, right? So which one is the smallest hump? So which transition state is the slowest? So which one is the largest hump? It takes the most energy. Which one has the biggest hump? H, F, or K? H. H would be the slowest step for transition because it takes a lot of energy to go up the hill to get to J. Right? Which one goes downhill the most? F or K? Which one drops energy the most? K. K is the fastest step because it loses the most energy. It takes the least amount of energy to do that. Does that make sense? Athena?
Yeah, can you wait for me to write this down really quick?
Yeah, take as much time as you need. The reason this occurs is because technically you will make G, J, and L, right? And the equation could theoretically stop at J, right? But it could also, the question could ask, for example, L, it could be the most major product because it could be a rearrangement of the thing. Make sense? So just know that the lowest energy one is usually the major product, while the least amount of energy is the minor product.
Why is H the transition state for the slowest step?
What's going on? Sorry.
Why is H the transition state for the slowest step?
Because that's the hump, right? It's transferring from J or G to J, right? It's going from here to here. It's transitioning. So H is a transitional state, and it's the slowest because it takes the most energy. It has to overcome that hurdle of energy. Does that make sense?
Yeah.
Cool. Okay. Ready for the next one? Athena?
Yeah.
You don't sound confident. What's up?
I was writing the last one still.
Take your time. There's no rush. Well, there's a rush. It's like 10:30, but we still have an hour. And 10 to go 2 hours. To the kids go.
Sorry, why is L the product with the fastest step?
Because you're losing energy, right? So you start off with E and you go to L. See how L is lower energy, has a lower energy state than E. It's so much easier for going E to L because it doesn't take as much energy, right?
Oh, for the initial.
Yep. So imagine if you had to go to the third, you had to go 3 flights of stairs, but it was also an escalator. The escalator would be more helpful, right? Because you're still doing the same thing, it's just you're using less energy. That's pretty much what's going on. Escalators helping, where you're at the same
Why
place.
would it be G then?
Why? Well, G is right there, but which one's lower, G or L? L. So that's why it's the lowest. Because it doesn't want to stop at G. It wants to go to L. Because it's lower energy than in that one. Molecules are like us. They want to be as lazy as possible and have the least amount of energy to do anything. Okay. All good? Athena?
Yes.
This is the reset.
I don't know. It's just topic 5. I'm just giving what you guys give me. I don't have class. So. What is this? What's that word say?
So it's a carbon.
Carbon with a negative charge. We have the stability, right? So always the most stable thing is going to be a benzoic structure because of resonance structure. Yep. Benzene has lots of resonance.
It's for the negative charge over
Yep.
there. Is
Exactly. Okay, hint, hint, wink, wink. Don't touch benzene. You do not touch benzene in O-CHEM 1. You walk away. If there's a reaction that involves benzene, you don't touch it. You touch this carbon right here. That's the only thing you touch. You don't touch any of that. Because other stability, it does not react. You have to use extremely specific solvent to react with benzene, which is O-CHEM 2. But it's like the later half of O-CHEM 2. So there we go. Following that, we have allylic, which is this guy. The reason why this is very stable is because we can keep moving resonance structures, right? We can keep moving that guy here, make the double bond over there, make the negative charge move back and forth. Resonance stabilizes things. That makes sense? Okay. Next comes the things you actually need to know for SN1, SN1, SN2, E1, and E2. And that is the most stable place for anions to be is on a primary carbon, right? Which is a primary carbocation, carboanion.
right, and it goes primary, secondary.
Yep. And lastly, tertiary.
Where's the methyl?
Technically, primary would be a methyl. It depends.
Do you have
Depends where.
methyl?
Technically, if you technically right here, this is a methyl. That is a methyl missing a carbon. That is primary. Thinking.
Isn't carbon
You could also draw it like this if you wanted to. I just draw it like that because that's how I see it in my head. But
methyl would be at the front.
yeah, it would be primary because it's only one attached to one other carbon. It's by itself technically, right? These two are exactly the same type of structure. Yeah. Why is tertiary the least stable for anions?
Because there's no room for the wait.
So anions means this means the carbon has 2 bonds, correct? It wants to form another bond, correct? What's going on here is you have tons and tons of hydrogens in the p orbitals, right? So all these p orbitals that are kind of cock blocking those electrons right there. Why do you look at you looked up when I said that word? What's up? What? Nothing. You're good. But yes, that's a good way of thinking. Is technically all the hydrogens in the p orbitals are cock blocking the new bonding to make it happy. So that's what's going on. That's why it's still the least stable. There we go. For carbocations, it's the same first 2, right? Benzene, benzoic, and allylic. But then it goes tertiary, secondary, and then lastly, primary. There's being here, we don't want bonds to form because it's a cation, right? It doesn't have extra electrons, right? So it wants to be protected from another bond. That's why it wants to be protected by the p orbitals. It doesn't want another bond. It kind of, it positively humanly would want bonds, correct? But it's still being blocked by the hydrogens, right? But being in those p orbitals, it's technically, theoretically, it's more stable this way because it's stealing the electrons, like not fully stealing, but kind of borrowing the energy of those electrons from the hydrogens. That's what's going on there. That's why tertiary is more stable. Mhm. Good. So how would you attack that positive right there? If it's being protected. Nucleophile, good. Which would also have to do what? Do backside attack later on. Because it's being protected, is it not?
Yeah.
It's being protected, so you attack from the backside. That's why backside attack occurs with that. But we'll talk about that a little more. You guys going?
Yeah. Thank you.
Of course. Good luck in your tests. I'll see you next week. Yeah.
Yeah.
Yeah. Okay. Now we have carbo-radical radicals. And same thing, always benzylic and allylic. However, it follows the exact same stats as cations, which it's always tertiary, primary, or secondary, and then primary.
Tertiary, secondary.
Yep. And there's this last one, which is directly connected to a double bond. This is extremely unstable for radicals. When you have, like for example, it looks like this. You have a radical connected to a double bond, that is extremely unstable. The reason being is it can't form an extra bond, correct? Well, all you need is one more electron to make a triple bond, or one more electron to make a bond, right? So it's going to want to take a single radical electron from something to make it happy. That's why it's very unstable. Because it doesn't want to be, it doesn't want to exist. It wants to destroy things to get an extra electron so it can form a bond somewhere. Okay. Athena, you good?
Yes.
Cool.
Yeah.
Cool. Okay, energy diagram. So we have compound C, and as it can do two reactions. It can go and complete and make compound D, or it can make compound E. Which one is it more likely to do? Make compound D or E? Which one's a lower energy state? D. This is the lowest energy, which means it's the most likely to occur, correct? So we're going to say that we already eliminate B, C, and D. Because D is the most likely to occur, the most to be made, because it's the least energy, it's the least amount of energy doing it. So which one is the second least amount of energy?
Wait, I have a question.
Yeah.
Wait, so D is the most concentrated?
At equilibrium, after everything's done, you would have more D, because D requires the least amount of energy to make. Does that make sense?
Yeah.
That's why you'd have the most of D.
Okay.
That's why you have D here, D here. So which one has the second lowest energy? C or E? C, right? The second most, the little on the tail, but this is a little lower. E has the most energy, which means it's the fewest we made. So the answer is E. So D would be a major product, and then C would be a minor, and then technically E would also be minor, but it would very rarely exist because it's so much energy to make. You got any questions on 115 yet?
Yeah, I just have a question on this.
Give me 1 second, guys.
Is there like good way to remember when and when to not calculate?
Okay, back. You guys understand number 4?
Yeah.
Athena?
Yes.
Also, I feel like I don't understand why, but I understand
Why? Okay.
it makes sense. Like, I don't understand why D is the lowest, but I understand.
Why it's the lowest energy? Because
Sorry, why it's the highest concentration.
so let's say I have a reaction, correct? So let's say you have 3 options. You have 2 options, right? To get to class. You can go the long way or you can go the quick, easy way. Which would you prefer? Personally, the quick, easy way. Molecules are the same way. They're going to go the easiest way that takes the least amount of energy, right? So from C to D, right? It does have to overcome that hurdle, right? But it loses so much extra energy, correct? That it kind of counteracts that. So after it reaches equilibrium, which is the key part right here, D is actually going to take the least amount of energy, right? So most of the time, anything, if I have C, it's going to mostly want to become D, not at all become E because of that. So if I have this equation that could either become E or D, most of the time it's going to become D, right?
Because the
Most energy being released, it has the lowest energy total. So it's more exothermic, which comes to Gibbs free energy, right? Where you have or delta H, which is going to be heat energy. Gibbs is going to be delta H minus delta S T, right? We assume that everything's going to be, this is going to be like the same, right? So amount of energy being released, exothermic, endothermic, would determine that. That's how you know. Because we don't tell exactly what, so we can assume that delta S and T are the same for all 3 of them. So anything that's exothermic is going to have way more. Yeah. So yeah, that makes sense. That makes sense now? Cool. Okay, to find the terms. Hopefully you guys know this from being in chemistry for about 2 years now. Reactants are going to be on what side of the arrow? Products are going to be on what side of the arrow? Good job. What does synthesis mean? You're going to be adding something, right? Adding or making something, right? Making a new product. And intermediate is something that is created and immediately destroyed to continue on, right? It's just basically a rearrangement of something.
And they're typically used in S and S1.
S1 has, yep. Exactly. They have an intermediate. Mechanisms is the step-by-step interactions, which we'll see right now. There we go. Let's make it bigger. That's a bit too big. Okay. Can you see?
Yeah.
Athena, can you see?
Yeah.
Okay. So we have excess hydrogen peroxide. Good. This means we are using energy and light. We're using energy and light to move this reaction forward, correct?
Yeah.
Okay. So, do I touch benzene at all? No, you always walk away from benzene. So cross benzene out. What's the only thing I can touch then?
Oh, just the.
Yep. So what you get is you're going to get and you'll make you'll kick off one of the hydrogens coming off the benzene. Make H2, that's this, or you don't like that way, you can do this instead, H2O. But that is the overall reaction. Now let's do step by step. It tells you homolytic. What's that mean?
Hobolytic means that it creates radicals.
Creates radicals. Half an arrow, half an arrow. There you go. Does that make sense? Yeah. Okay. So I have my benzoic carbon reacting with one of these guys. This guy's got 3 hydrogens. So how close is hydrogen and carbon and electronegativity? Nope. Very similar. Which is why a bunch of CH molecules like this, right? Is nonpolar because it's even sharing electrons all the way across the molecule. Like fat and lipids are non-soluble, non-soluble because they're nonpolar. So carbon, hydrogen are homolytic. So when they break apart, hydrogen gets 1, and that carbon will also get 1. So now I'll move this guy over here. Hydrogen with 1 little dot. Well, how many electrons makes a bond? How many electrons are in 1 bond? 2. So what's 1 plus 1? These guys come together and you form water, and you form radical.
Wait, why are you drawing the radical above the benzene if the radical is going to the OH?
Because what's going on here, let's undo. Okay. So how many electrons does this thing right here want to know? How many does it want? How many electrons?
1.
Wants 1. Wants 1 electron. The only way to get 1 electron is to make a radical. Radicals need radicals to make them happy. Does that make sense?
Yeah.
So you can't touch benzene. So all you have left is this methyl group, right? So we're going to form a radical because carbon and hydrogen are homolytic to each other. They're very similar in electronegativity, correct?
Yeah.
So you break this bond, carbon will get 1 electron, hydrogen will get 1 electron, which will make a hydrogen radical. That radical will interact with the OH radical, making water.
Okay.
And then you get a radical benzoic carbon. Is it okay to have a radical benzoic carbon? Yes or no? Is this molecule stable?
Yes.
or no? Because of resonance. So in reality, I misplaced the boxes. It's actually going to be this instead. this is actually more stable than water. Because it's a benzylic radical. It's not. I know, it's stupid, but that's what he says.
You sure it's not like, 'cause
I agree.
maybe I'm wrong, but like, what if like.
It
the
should be-
hydrogen deprotonates, and then the OH plugs in where there's that extra radical? That makes sense.
I agree with you. I'm just telling you what the key says. It's the only reason I'm trying to justify the key, right? I'm not trying to step on Grubb's toes. But that's what the key says. Most likely I would have put in the opposite boxes because technically this is a radical, but it is a stable molecule. They're both technically stable. But that's just how it is. Grubb's not always right, but it's a possibility. Right? Bastard. Never mind. I misspoke. Because we're gonna see down here. Never mind. I'm tired. It is a radical, so it's going to be here, but it is stable. Water is going to be here. Because we're going to use this guy down here.
It's a stable one.
It is a stable radical. So here's my benzylic radical. And it's going to interact with OH, correct? We know OH is going to make an OH radical, correct? We can kind of just do this. And hey, what do those two guys have in common?
Radicals.
So you can inform this.
Right, that was what I was thinking. Step two, but I was-
Wait, why did you cross out H2O2?
Because we know H2O2 is going to make these guys, right? So I just cross it
Okay.
out and just know that this is now that's a solution. I just kind of made that occur. Does it make sense?
Yeah.
Okay. You have to read steps very carefully, right? I agree with you. You probably think you would do that in step 2, but you don't because you have to make a radical, right? So it's propagation. That's what's going on. That's how you kind of tell it's what's going on here. Yeah. But that's how you do step-by-step equations, that type of mechanism like that. Hey, this guy looks like fun, doesn't he? Okay. So Grubbs is nice when he first goes over mechanisms. He gives you the answer most of the time. So if you look right here, you have this guy right here. He's reacting with himself within light to make that product, that molecule. So where can you find this guy? 2 of these guys onto this guy right here. Where do you see that occur? Do you see that those 2 guys make up this guy right here? Do you see that or no? Okay, let's draw it out differently.
Oh, yeah. But not including that bond.
Yep, not including that bond, right? So what it means is one of these bonds breaks, right? So what bond break? The bonds between the carbon and a nitrogen.
It's what's
Yeah, no, homolytically, because that right there is a radical. If you zoom in close enough, that is a radical. So it's a homolytic bond. So now I have nitrogen double bond to nitrogen, and both of them are radicals. Do radicals like to be next right on top of double bonds? Yes or no? Is that stable? Is this stable? No. What happens is it takes 2 electrons and it forms a triple bond instead. Because that's way more stable than a double bond with 2 radicals. Because radicals do not want to be a part of a double bond. They want to be next to next to, but not part of. Does that make sense? So that's how you form a triple bonded nitrogen. I think that makes sense.
Yes.
Okay. So now I'll draw this guy over here so we can see what he looks like. So this radical is on what type of carbon? Is it a primary, secondary, or tertiary?
That is on a tertiary.
Tertiary, very stable, right? So there's no rearrangement. Okay. It interacts with this guy, BUSNH. We don't touch this guy. We don't touch this guy. We don't touch this guy.
Is that C for
It's C4H9. It has 3 branches of C4H9. The reason I know we don't touch those is because this guy becomes this guy. What is the difference between the 2 purple boxes?
the hydrogen was deprotonated.
That's a radical. So homolytic bond, correct? So you'll see this. There you go. There you go. So we have this radical hydrogen solution, correct? What's a hydrogen radical want to bond to? The other radical we just had. So you'll form this guy. You'll form that. Does that make sense?
Is that NC plus H?
That's no, not plus. It is a. I'm trying to draw it the best way.
Oh,
It
it's
is-
the bond.
Yeah. It's not plus. It's 2 different carbon bonds. Technically, it's a methyl. That's methyl too. Okay. This makes sense?
Yeah.
Cool, cool, cool. Okay. Can I erase all this?
Yeah,
Athena?
Yeah.
So now we have this guy reacting with this guy. This guy, purple guy, or pink guy becomes pink guy. Not pink eye, pink guy. So what happens here? What happens? How did the pink box become the pink box? The leaving group left, right? But did it leave in heterolytic or homo? Homo, because we still have a radical. If you notice, if you have a radical, you almost always have a radical. It's really hard to get rid of a radical. So now, doing this, bromine radical is in solution. What does bromine radical want to bond with? Radical, radical, radical. What occurs? Make BU3, SN, BR. You basically just add the BR right there. This guy becomes that. That's what occurs. Does that make sense? Athena?
So where did the BU3?
That was this guy right here, the red box. This is the BU3 SN.
Okay. And then the radical on the SN binded to the radical on the BR.
Yep.
Okay.
Okay, you guys ready?
Yeah.
Athena?
Yeah.
Radical here. Radical is on a primary, secondary, or tertiary carbon. Is that stable? Yes or no? No, it is not. So what do we do? We have to move it. The electrons move, right? The ring closes. And you get a cyclic structure. Nope, the radical is right here. The radical transferred to a secondary carbon, which is more stable than primary. That make sense? That's why it's there. So the ring closes. We still have BU3 SNH in solution, correct?
Yeah.
Forms homolytic. Takes a hydrogen, and the process goes over and over and over again. What this is trying to tell you is as soon as you make a homolytic bond, you will always have radicals in every single product because you can't get rid of radicals. Does that make sense? That's why radicals are very dangerous in the human body. That's why people like want to take antioxidants and stuff, because those are the only things that can stop radicals, is antioxidants and such. So drink your wonderful pomegranate juice. Do you know they got sued once because they said they could stop cancer? They said they could stop cancer and they got sued because people who got cancer drank it and they still got cancer, so they sued. So now it's like almost as good as stopping cancer. So in the bottle, it's so stupid. Well, if you look at Red Bull, it gives you wings. Did you see how they spell wings? This is how they spell wings. With 2 eyes. Red Bull gives you wings. Go watch the commercials or read the bottle. It spells wings like that. Because someone jumped off the building after drinking Red Bull. It's like, it didn't give me wings. I can sue you. Because it's false advertisements. But now it's 2 eyes. The company goes, hey, you're just stupid because you didn't notice 2 eyes there.
That's so dumb. They have to do that.
What do you hear about the person who's suing Pop-Tarts? Because the strawberry Pop-Tarts doesn't have strawberries in them?
Dude, someone's gotta sue Subway. I heard something about Subway's tuna.
It's not really tuna.
Dude, there's no tuna in Subway's tuna.
It's not. It's
And
just
I
tuna.
ate it
Yeah.
pretty much all of freshman year every single day.
Yeah,
I found out.
It's not tuna. Most time it's hard for fish. Because most time for fish, like yellowtails like that, it's not the fish because they're too expensive.
Yeah.
It's a cheap knockoff. So yeah,
But it's still fish though, right? And
It's
I was
still
like,
fish,
it's not
yes.
tuna,
I don't know exactly what fish. I don't eat fish, but it's very similar fish.
but it's- Gross.
So here we go. So here's a molecule. Predict the major organic product. So bromine is what?
The leading group.
It's a leaving group. Does it want to form a homo or heterolytic bond? What does it want to form?
I don't know.
Is it more electrophilic or less electrophilic than carbon?
It is
Way more. So it wants to form a heterolytic.
No, wait, wouldn't it be?
No, it's electrophilic because it's electron loving. It's going to steal electrons. So you give it two. You get both of them. So then you get this. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So you get 2 with negative charge. And the bromine leaves. It's got its negative charge, it's 2 electrons, it's gone. That make sense?
Yeah.
So your product will have 7 carbons and 14 hydrogens. You guys remember the very first concept you guys learned? Is that going to form any double bonds? Is it?
What?
You guys remember that one concept you guys learned? For EU, to figure out how many everything has double bonds or not?
Yeah.
EU, what's EU that? Athena, how do you remember how to do EU?
Is that the 1/2 of
Yep.
C?
Huh? Yeah. Want something else? Easier way. Major is what? The most stable, which means it has the least amount of energy. What is the most stable molecule in chemistry besides benzene? We learned it a lot last exam. What is the most stable compound? Not benzene, besides benzene. It has 6 carbons that forms a ring. Hexane. Form hexane and put an extra methyl group. That is your major product. You know this because what occurs is the ring closes on itself. Oh, sorry, my bad. This is not a negative, be a positive. Positive here. The negative reacts with a positive and you form a hexene ring. It closes on itself. Huh?
Rings are always more stable.
Rings are always more stable. So that's why you form a hexane with a methyl group. That makes sense, Athena?
Yes, kind of.
This example. Know this example. He will put this on every test. He loves ring closing. Hint, hint, wink, wink for O-CHEM 1 and 2. He will make the rings close, open back up, and close again.
Wait,
Just despite you.
how is it positive?
Wait, isn't there a positive charge that goes on the hexane ring?
There would be. That's why these guys right here will donate a hydrogen. What's up, Athena?
Wait, why is it positive on the end?
Because bromine left. It's being electrified, which means it's taking the electrons from the hydrogen, the carbon,
Oh, okay.
leaving a positive charge, which will react with the negative charge from the double bond, forming a ring-like structure.
Got it.
Some of you are probably asking, why didn't we form heptane, correct? Does a carbocation want to be on a primary or secondary? Carbocation. It goes tertiary, secondary, primary for positive. Would you want to see a 3-legged cat, a 2-legged cat, or a 1-legged cat? 3, because it only lost 1 leg instead of losing all its legs. All right, less depressing thing. So we're going to move the carbocation in this thing called carbocation rearrangement, which just basically means we move the positive charge over 1. So it will look like this instead. 1, 2, 3, 4, 5, 6, 7. Positive bond goes here. That negative one will go here. That's why, hence why you make a hexene with a methyl group coming off. To attach that 6th carbon instead of the 7th carbon. Does that make sense? Athena?
Yeah.
Cool, cool, cool. Make sure I'm still recording. I am. Good job. Okay. Bromine. I love it. Bromine does what? Bromine leads. Is it electrophilic or nucleophilic?
By itself.
What bond to carbon? Electro. It wants to steal the electrons, right?
And when it breaks off.
Yep. So now we have a carbocation, which is this guy right here. So we have 2 pathways when we're reacting with ethanol. Ethanol can act like a nucleophile, or it can act like a base. So in product A, it's going to act like a nucleophile, which means we're going to add it to the product. We're going to add it. Correct? So let's draw this out. Which one's more electronegative? Oxygen or hydrogen? Gets both of the electrons, correct? In that bond. Yep. So it's going to then make a negative charge bond here, which is going to react to the positive charge, giving you that structure. Oops, my bad. Sorry. It should be this instead. Make an ether. My bad. It makes that for A. Because the negative charge on the oxygen is going to react with the then positive charge on the carbocation, forming that structure. Does that make sense? Okay.
Are you still there?
I'm still here. I'm just waiting for you guys to tell me when you're ready for part B. You guys ready for part B?
Oh, I have no idea.
Athena,
What'd you say?
how do you do part B?
I thought it would be the same, but
No, it is a base. Go back to 115. What's base do? What's a base?
accepts the positive. charge.
Accepts a hydrogen, right?
Yeah.
So let's draw this guy a little differently.
Wait, how are we supposed to know that A is different from B? Because it's the same, it's reacting with the same thing.
Ethanol acts as a nucleophile, makes product A. Ethanol as a base
Okay.
makes product B. It kind of tells you that's not the same. So we either need to give a hydrogen or an electron to the ethanol group, right? Because Lewis acid, Lewis base, or Bronsted Lowry acid, Bronsted Lowry base, correct? So where does the hydrogen come from? Is there a hydrogen anywhere close to that positive cation? No, we're going to pull from one of the methyl groups instead. Correct? So going on here, you can pick, you have three options, they're all the same, right? But hydrogen's gonna break away. As it breaks away, the carbon's gonna take both electrons. Reason being is we want a an ion for hydrogen, right? Because we can take the electrons of OH, right? Form a bond with this guy to make water. Because a byproduct for every acid-base reaction is water, correct? Or hydronium, right? But water is usually something, correct? So we just made a water. So what this guy right here becomes is he becomes this. There's a positive charge here with either a negative charge on that carbon, and or this carbon. It doesn't matter if you chose red, green, or blue, they are all the same thing, right? But now I have a negative charge and a positive charge. Where do the positive carbon, where do the negative electrons want to go? They want to go towards the positive, right? How do I do that? I form a double bond. To make the carbon happy, right? If I form a double bond, you get this. Bond like that. Correct? Do you see that?
Yeah, what are the?
Because it's going on
Where the protons break off?
any of the methyl groups. Here, here, or here. You can choose either one.
And then that bonds with the OH.
Gives you water, right? And then you just have this random radical as well, not radical, but ion. We don't care about because we care about what this guy makes, not what this guy makes.
You can turn any of the hydrogen bonds that are there.
Yep. Yep. So that's what happens. Does that make sense?
So
Athena?
Yeah.
Very confusing. I get it. I know. It sucks. But that's just what it is. That's why it's a review. And since it's hard, guess what he's going to most likely do? This most likely will probably be in the test. Because he is a butthead. Hey, this is like fun.
Shane.
Yeah.
This is recorded.
Yeah. Cut it out.
Yeah, I gotta say.
Okay. See ya.
Yeah, thanks for the review. Are you gonna do it next week?
Probably not this week. Next week though. Yeah. Probably next Monday into Tuesday.
Yeah, just text me.
Yeah, we'll do. Okay. Ready, Athena?
Yeah, is it just me now?
It's just you.
Okay.
Oh. Am I missing a question? Control.
All the numbers are off.
That's fun.
Yeah.
Yay. See ya. Okay, well, let's do this one first. Let's make this 5 and this 6. Okay. We have steps A through D. So this is our reactant. This is our prod. What happened, Athena?
We formed a double bond and lost a group, so that would be elimination.
Exactly. If you ever form a double bond, that is elimination. elimination. Good job. Okay, ready for arrows?
Yes.
Everyone's favorite part. Oops. Nope. Zoom in a little bit. Scroll up. Okay. This guy becomes this guy. What's the difference?
They're the same.
No, no. It lost this.
Oh, I thought you meant between the two groups.
No, between that one and that one. It lost a hydrogen, correct?
Yeah.
So this bond breaks, oxygen acts like an electrophile, making it a negative charge. We then have nitrogen giving up its bonds to form a bond with hydrogen, giving us this guy. So far, 2 arrows. 2. Okay. This making sense?
Yep.
Okay. Okay. So now we have, let's do a different color. We have this guy, and he gets added to this guy. It's an addition, correct?
Yep.
However, one of the sulfurs becomes negative. What's that mean?
It gained an electron.
So break one of the bonds. Let's break that guy right there. Arrow goes there, right? Which makes that sulfur negative, that carbon positive. We would then take 2 of the electrons right here, form a bond, and there we go. That's another 2 arrows. That makes sense?
Yep.
What does Me stand for?
Methyl.
Methyl. So where's that methyl group come from?
The H3C.
There we go. So iodine is a halogen, correct?
Yep.
So breaks, steals a bond, making the guy positive. This guy will use the electrons here to go there, make a methyl group. Another 2. Okay. This making some sense?
Yeah.
Okay. So now let's do blue. This guy right here, where's he come from? Because there's nothing added in part D, right? So that blue guy, I just circled or boxed, came from this molecule. Where is he?
What do you mean? Where is he?
So this guy right here
Mhm.
has to come from this guy.
Right.
He's somewhere in the molecule, correct?
Yes.
He's right here.
Okay.
So how do I go from this guy to this guy?
You move a double bond from the S to the O.
Nope. You break this bond, giving that oxygen its self. So that breaks off, you get this structure. Negative oxygen, bonded to S, bonded to S, CH3. Correct?
Yeah.
Okay. Well, we had to make a double bond with oxygen because right there. So that will go here, form a double bond, which will move the arrows here. Correct?
Mhm.
You're wrong. I don't like when he's wrong. This will make that sulfur negative. Right? That then will pull that hydrogen away. Because that hydrogen will break the bond here and go there. So 1, 2, 3, 4, 5. I made 5 arrows.
Just on that last step.
Yes, he's counting 3. He's simplifying a lot. I don't like it because it's not how he teaches you guys. He says 9. I'm getting way more. So, but he's saying 9. But that's what I would do. I hate curvy arrows because everyone does them differently. It's very annoying.
Yeah.
But that's how you would approach the question. If you can simplify it with 2 less, you can. Getting 3, which would be 9, but I need the 2 extra arrows to make the double bond and steal the H. So, whatever. Okay. So 5 is 9, 6 is elimination. What is the most appropriate description for 7, which is step A? Wait, what?
That would be acid base. Right?
Yeah.
No?
Yes. Because you're losing a high hydrogen, correct?
Right.
Which is an acid-base reaction. So this right here is acid base. What's B? Addition, elimination, rearrangement
Addition?
is addition. What about C? It's substitution. Because I'm substituting it to there. Addition is usually substitution, but very large molecules. Substitution is very, very small, usually like a methyl group or an ether or something like that. Very, very small molecule.
Okay.
Okay. And lastly, D is what? Make a double bond.
Elimination.
Elimination. These are the types of mechanisms you need to know. Substitution and elimination are just your SN1, E1, and E2. SN1, SN2, E1, E2. Addition and acid base is something you guys should have known from like Chem 115 and such. So, that makes sense?
Yep.
Which I just answered all those. Step A, acid base. B is addition. Step C is substitution. Step 9 or step D is elimination. Yeah. In the urea cycle, a biological pathway for moving ammonia, a toxic metabolite organism, conversion of blah blah to the blah blah forms blah blah in an E2 pathway. Draw the structure of the two products. So E2, what's that mean?
Elimination.
Eliminating something. So what's going to happen? I'm going to make a what?
Double bond.
Double bond. So let's look. This goes away, making electrons on that carbon right there. Correct? Which is how I get BH. That's that step right there. Correct?
Yeah.
Okay. This arrow right here shows the breakage of that molecule. So, what this means, this arrow separates these two from each other. So those are two products. Does that make sense?
Which arrow separates them?
This one right there. Let's use black because it's easier to see. This one
Okay.
right there. So let's do the red one first. We got C, C, CO2 minus. We got H, we got CO2 minus. We got an H, and we got double bond between because this arrow right here made a double bond form right there. So there's our first product.
So you were just drawing out the second half?
Yep, this red box.
Yeah.
I just drew it out. Does that make sense?
Mhm.
Yep. So I'm going to erase all the red stuff because we don't need it anymore. Okay. This arrow right here forms a double bond right here, which then destroys this double bond moving up here, making the electrons, make that go away, get electrons. So you'll have this structure. Typically that's dashes up, N, H, two dots up here. We have an N, that's H, two dots, and then double bonded N, H. There's your second structure. The blue structure is this black structure right there. Does that make sense?
Yeah.
So basically, what number 10 is trying to teach or test is if he gives you a big molecule, you need to know how to break it based off of arrows. So like I said, this is the key arrow, breaking the molecules in half, giving you two different products. There you go. Okay.
Sorry, I'm still writing it out. Oh, shoot.
There you go. So you have, what, 250 questions or 200?
Apparently it's just 100,
Okay, sure, whatever.
which it makes no sense, but
It is what it is.
so basically you're just rewriting the molecule.
Yep.
Showing how, like, after the arrows are gone, what it would look like.
Because he already does the arrows for you.
Right.
So instead of you doing the arrows, he does the arrows. And you tell him what the arrows do.
Okay.
And I
That's
know
easier.
double bonds are formed because it's an E2 reaction. Sorry, I didn't interrupt. What's up? Okay. 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 Ready for the next part?
Yeah, I'm just writing it out.
Take your time.
We're kind of almost done.
We are almost done. I don't know if I can do substitution today. I might do it sometime.
Yeah, I would say do it another time.
Do another time. Okay. So, only topic 1, or topic 5. Okay, let me know when I can erase.
Oh, you can erase. I'm just writing the next problem right now.
Okay. Okay. Delta H, delta S. Oh no. What's that mean? Love when Cam 115 comes and bites you guys. That's the butt.
Literally.
Love it. So beautiful.
Okay.
Okay, ready?
Yep.
So knowing nothing else, going from A to B, which one's more stable? Stable.
B.
B. Why?
Because it's a closed ring.
To close ring, more importantly, it is what? What type of ring?
Benzoic.
Nope. Not benzene. It's hexane.
Oh, shoot. Okay.
It is a hexene ring. More resonance is also available because of these guys. So B is way more stable, which means it's more likely to occur, correct? So Gibbs free energy has to be negative if we want A to become B. Does that make sense?
Yeah.
Gibbs free energy is delta H minus delta S T. Is temperature relevant at all here?
No.
So we ignore it. So what is the easiest way to make delta G negative?
Have both signs be negative.
Negative? Negative. Good job.
Wait, hold on. Why did we want delta G to be negative?
Because delta G is spontaneous. So there you go. This is spontaneous, meaning that this guy requires less energy to make. So we want to become him. That's all it means. Which I don't know why he's doing this. It's more biochemistry than it is organic chemistry, but whatever. That's it. Ow. Hey, we're back. We've seen this guy before.
Oh my god.
What? It's not a lot of work. It's fine. So we make two of them. Make this guy. So break this. Boom. Break that. Boom. You get one, and you get one. Everyone gets one. So get this. And a little radical. Super adorable.
I'm glad you have energy right now.
What? Why?
What do you mean, why?
I'm not full of energy. I just had a down, a bang, and then a Mountain Dew. So I'm
Wait.
tired.
Can you go back up to the that one? So you have an arrow going to the end and okay.
You're
Yeah.
from a homolytic bond. Because nitrogen and carbon are close enough, they can form a homolytic bond. So basically, anytime you see this guy, it's homolytic. It's popping up 3 times, which means he's definitely going to be on the exam. Intent, like we most likely. Do I know? No. But knowing grubs? Yes.
Okay.
Do you know what this pH is?
Mm-mm. No.
I don't know either. I don't care. What's this
Okay.
S right here?
Sulfur,
Okay. What's this H?
hydrogen.
We saw with the BU SN H, right? What popped off? What does this guy right here want to be happy? He wants what?
Electron.
He wants 1 electron, which can come from a radical hydrogen. So you're gonna make a radical hydrogen to make this guy. So you'll get pH S radical. Does that make sense?
Yep.
Okay. I'm gonna erase, move down just a little bit.
Did you say it's PHS with a radical?
Yep. pH S radical. Actually, I'm gonna move down a little bit more. So boxes. There we go. Beautiful. Okay. So you make this guy right here. How does this guy and this guy differ?
The R group is gone.
R group is gone, right? So what occurs? Oxygen gets 1, nitrogen gets one, correct? Then the sulfur will give this 1, gives that carbon 1. So now the oxygen bond breaks, gets off, giving this. Bada bing, bada boom. Radical form of that. That puts a radical on that sulfur. Those 2 radicals team up. And since this nitrogen has a radical on it, this carbon has a radical, they form a double bond, making a stable pseudo benzene. Does that make sense?
Yeah, somewhat.
Okay. Any questions from Vaughn?
No, that makes sense.
This arrow right here, it's leaving. So what is it exiting from this box? A carbon and 2 oxygens, correct?
Yeah.
So here is the oxygen. Here is the second oxygen. So this entire green box is leaving. To do this, they have to break the bond between the R and the carbon, right? That bond right there breaks. You get half of one, you get half of one. And then since there's 2, we form a double bond. So C double bond O, C double bond O, and that's where that guy comes in. So we're left with a radical R. Now I have this radical R. He is interacting with H, S, pH. How does this guy become this guy? Athena?
By losing a hydrogen.
You get one, you get one. The hydrogen radical bonds with that, and you get that. And then it starts over and over and over again. Basically, if you have a radical, you will always get a radical. It's a never-ending cycle. That's the biggest takeaway from this topic review. Does that make sense?
Yeah.
Cool. Almost done. Nice. We are number, oops, we did that one. We just that one. Number 10. When comparing the reaction of 2-methyl-propane with either Cl2 or UV light and Br2 UV light, which of the following statements is true? So which one is more selective? Chlorine or bromine?
Bromine.
Why?
That's just what he told us in class.
Which one's bigger?
Bromine.
Bromine's bigger. So bromine has to be more selective where it pellets its junk or its trunk. Since it's bigger, it has a harder time attacking molecules. So it has to be more selective on how and where it attacks. Does this make sense?
Yep.
Cool. Does it make any sense? Bromine is a truck. If you try to park your truck, you have to park in a place where you can fit your trailer bed. If you don't, someone's gonna hit it, your truck's dead. So you have to be very selective of where you park the bigger molecule. So, A.
Wait, but bromine is less reactive?
It is.
Oh, because it
More,
doesn't
more
react with
selective
acids and things.
means
Yeah.
less reactive. Yes, because it's less likely to react with stuff. Because it's more selective. This is a contradiction. Yeah.
Okay.
NBS. What's NBS do?
I'm not sure.
Mechanism you guys need to know. NBS will form a radical. It will pull off a hydrogen to form a radical. So looking at these guys, we can eliminate A and E because we do not add bromine. Now, B, C, and D are our choices. Which one looks different?
Which one looks different?
We've seen B, D, and C.
Oh,
What's
C.
the biggest? Yep. Don't remember the double bond. All we do is form a radical. So between B and D, which one is more stable?
Oh, B.
Why?
Because it's on a carbon that's outside of the ring.
Well, yes, but it's on a tertiary carbon, correct?
Yeah,
But also near a allylic. It's allylic and tertiary.
that's what I was trying to.
Yep.
yeah.
So it's allylic and tertiary. Very, very, very important. But just know NBS will make a radical and it will not add bromine and it will not destroy double bond. You just have to know it. That B right there is not bromine, it's boron. So that's why A and E are gone. Does takes this hydrogen, kills it, gives you one, and it gives that one for you. Okay. Order reaction depends on what?
The rate determining step.
Please form 115 or something.
Wait, okay, yeah, I like barely, like very vaguely remember that.
First order, zero order, second order. Stereochemistry? No. Elementary step? No. Concentration of reactants? Don't care. Temperature? That does affect it, but doesn't do anything. Concentration of products? Don't care. It is the rate determining step. Because the rate determining step is the step that determines the order of reaction. Chem 115, let's come back. Fun times.
What should I say for the reason?
Because by definition, the reaction is dependent on the rate determining step, because that's what determines the rate. And the rate helps you figure out the order. You have step 1, step 2, right? You make A plus B gives you C, and we use C plus D gives you E, right?
Yeah,
And the order reaction is A plus B. So number 1 is a rate determining step. Well, 2 is not. Just stuff from 150 to T. Come back. It never leaves. Let me know when you're ready.
I'm ready.
Okay. What's this?
Are you asking what it is?
Yeah, what is it?
The leaving group.
No, it's a radical. It's got
Oh,
1. So what's that mean? We always will have radicals. So, yay, fun times. Okay. So basically, we're always gonna have a radical. So this bond breaks, you get 1, and you get 1. is this radical happy?
No,
Why not?
because it wants another one.
What's another one? Is it stable though?
No,
Nope, 'cause it's not allylic. So it's going to do a change, conformational change, correct? So remember that radical. That radical is going to go somewhere else. And how we do that is we kick CO2 off. So CO2 is an oxygen, a carbon, and an oxygen. So how do we give that oxygen another electron?
by moving the double bond.
Kick it off. You get a radical, and you get a radical. Because a radical is involved, you always have to have a radical in your products. So you don't move the double bonds. You make a double bond because you make a radical. This guy becomes CO radical, oops, single bond. Nope. O with radical. We use both these radical to form a double bond to make CO2. Are you ready for the hardest step? Come in, ready to proceed.
Oh yeah, I'm ready, sorry.
Okay. So how do I go from B to A and make this guy? What happens?
You add it, well, you use the bromine that has the radical.
Okay. But that's over here. That doesn't involve anything. But kind of you do. But basically what goes in this box is this molecule. Because that molecule, right, when it reacts, is going to form reacts. You get one, you get one. You will form a bromine radical, which will interact with this radical to make this. And then this will form that guy. So it comes back. And the reason it's there is because you're right. Technically, that bromine is still in solution. We have to show how it's in solution. So that's why it comes back. Does that make sense?
Yep.
Cool. Good, because I hate radicals. Radicals are stupid. I don't like them. So we looked at all these steps, A, B, and C. What's the overall reaction? What are the two things I made? If you remember, this guy, A, is just basically C. These two guys are the same, right?
Yeah.
So what left this never-ending cycle? What left? What left?
The CO2.
CO2 is 1. What's the other thing that left?
The bromine?
Not the bromine, this guy.
Okay.
Those are your two products because they leave the never-ending cycle. So that's what you put here. And CO Those are your major products. So the overall reaction makes those two different things, but that's how you make them. Is that? Isn't this fun? I love it. I hate radicals so much.
Yeah, this is not fun.
No, radicals are stupid. I don't like them. Okay. So. What goes here is bromination, right? Bromination occurs. Okay. So when bromine, when they break apart, homolytic or heterolytic?
Homolytic.
So you get one and you get one. What does this guy look like? Right? So now I have two bromine radicals, correct?
Mm-hmm.
I have to form a radical with this guy. So I break the hydrogen, you get one, and you get one. So I will make this CH3, C, CH3, CH3, radical, 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 bada bing, bada boom, and you make bromine. It's called bromination. Or substitution, because I'm substituting a hydrogen for a bromine.
Wait, so it's both of those?
No, bromination is an example. It's what it's called. Just like the it has two names. One's a very specific name, right? It's called bromination because you're adding a bromine. But in general, it's a substitution reaction. They can be specially like specialized in the term bromination. That make sense?
Wait, so which one is the product? The one with the radical?
No, this guy. This is the product. I know it's fun, isn't it? Basically, anytime you have bromine, right, and you have this triangle, that triangle basically means you're making radicals. So the major product is that. Does that make sense or no?
Yeah.
I know. I hate it too. Okay. So we have bromine and we have a triangle, which means we're making radicals. Correct? Okay. What do I not touch? Always walk away from what?
The benzene.
Don't touch that. So I have three options. 1, 2, and 3. Where am I going to add the bromine?
To the
Which
secondary
one
carbon?
would form the most stable radical? 1, 2, or 3?
Wouldn't it be 1 or 2?
Nope. 1.
Oh, because it's right outside the
Benzene.
benzene ring.
It's benzylic. So what this molecule will look like is benzene, bromine.
Okay, that one makes sense.
I skipped the whole radical part because hopefully by now you understand it. If not, come see me in person. But yeah. Oh, if you want to piss grubs off, do this instead. Draw a circle there in benzene. He hates it. I love it
Why?
because he doesn't like it. I know this because he shares memes on Facebook. So do it. We have a bromine and we have a triangle, which means radicals. So on this guy, we want to form a radical. So we have to find the most stable carbon where a radical can form. So we have carbon 1, 2, 3, 4, 5, 6, and 7. What carbon would be the best? Oh, and 8, technically.
Which carbon would be the best?
Yeah. There's technically 4 options.
I was gonna say 4 or 8.
Nope,
No.
that is the
It'd be
worst.
It'd be 1, 3.
Yeah, you could argue 1. So 1, 3, what?
7 and 5.
7 and 5. Yep. But all of those would technically be the same product, correct?
Yeah.
It's just flipped. So they're all the same. So let's draw it. I hate this, goes there. Nope. I don't like drawing this. This thing's awful. Go back. Okay. Wait, can I draw? Oh, so shady.
Do you think 7 would be the best?
7 would be. That's the major. But technically 7, 5, 1, and 3 are all pretty much the same thing. They're just mirror images of each other.
Oh, and you say there's 2 products on this one?
There's 2 products. Yep. I'm gonna draw it on 7. The key has it on 7, but technically you can argue for 5 and 3 and 1. That's one product. What's another one? How can I make an even more stable molecule? Because this guy right here is not the most stable.
I don't know.
So radicals want to be on allylic, benzylic, or tertiary. Are there any tertiary carbons on this molecule? Athena.
No.
What about that guy and that guy? Are they tertiary?
Yeah, so that's why I originally said to put the bromine on there.
You are correct. You would. But we have to do something with this double bond. We have to move it.
Is this that hydride shift thing?
So if we, or this is also resonance. So if we move this here, right, we get this structure. God, here, 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 here. I go back to kindergarten because I can't draw. Okay. So now we have the double bond here, correct? Which would make this carbon right here tertiary and allylic, which makes it the best. It makes it super good to have bromine on. Does that make sense?
Yeah.
So this would be your major, minor. Oh, bring it back up so people can see it for a couple. Okay, long enough. Let's pause the video. Okay, Athena, how do you do this one?
You paused it?
No. They can pause the video to see what I drew.
Oh. How do I do this one?
Yep.
Well, I thought you don't mess with.
You don't. You walk away. No
So
reaction.
there's no reaction.
Don't touch. No touchy. I can't spell touch right now. My brain's all over the place. No touchy. Cusco. Emperor Nubu. No touchy. Ready? The next one?
Yeah, I'm just trying to draw it out really quick. Sorry.
The benzene, just do this and put a circle.
I know.
Because Grubbs loves this. Grubbs loves this. Only being me because he didn't say hi to me this morning. Ran into him, he gave me a weird look, like he didn't know who I was, which it hurts. So I'll make him remember.
He didn't remember you when you said hi?
Nope. Hurts.
Mm.
Wait, what? Did he mess up his key? Probably. Nope. Oh, I have to backtrack on the subject. Okay. So let's remove that. Technically, we can do this. If you have NBS with this triangle, you can add a bromine. That's just the way the word works. I don't like it either. That's how it works. So where would I add a bromine on this guy?
Are you asking me?
I'm asking, well, you're the only one here.
No, I didn't know if you, okay.
Well, I mean, I could do Dora the Explorer and ask and wait for no one to respond.
Okay. What did you ask?
Where would the most stable radical?
Wouldn't it be on? Would it be on 2?
No,
Oh my God.
it can't be on a double bond.
Okay, then it would be on 1 or 4.
Yes, exactly.
Okay, so it wants to be near a double bond.
Which is near, but not on.
Okay. Does it matter if it's 1 or 4?
Because they were saying. Switched. You still hear me? Athena?
Yeah.
Okay. Just make sure I switched headphones. Just make sure I'm being heard. I have a mouth and I must scream. Back up. Oh God, what did I do?
I think there's only one. Yep, there's only one problem left.
What
Or like
did I
mechanism.
go back to this monstrosity right here? Okay. Ooh. So we got to draw arrows. Fun, fun, fun. Arrow questions. Okay. The molecule is called dead. Same. That's my new favorite molecule because it's dead. Okay. What is the difference between dead molecule and not dead molecule?
There's a group added to it.
Group added, and we're missing a double bond here. Right?
Mhm.
Okay. So what occurs is bond breaks here. Electrons go to this nitrogen. These electrons go to that nitrogen. So far, 2 arrows. We then take this guy, move him over here. Let's use green next. So this guy becomes this guy. What did he miss?
Hydrogen.
Hydrogen. So he he lost a hydrogen, right?
Yep.
So bond breaks, you get both electrons. You take the electrons here, steal a hydrogen. 2. Let's use pink. Over here, we have step 3. Okay. Ugh, fine, sure. So what happens in step 3 is this bond breaks, nitrogen gets the electrons, and the electrons here bond to this ppH3 to give you that. So 2 are there. Step 4 and step 5 happen simultaneously. So let's do step 4 because it's in order. Cool. Let's do blue. So now I have my nitrogen from here to here, right? And then what's the difference between this molecule in the box and this molecule in the box? That guy goes away. So what happens is the bond here breaks, oxygen gets 2 electrons, use the electrons here to bond to the hydrogen, which means there's 2. Now, step 5 occurs here, in which let's use I don't know, orange. So this guy is this guy right here, and it has added this molecule. Well, this guy is right here. So to make that occur, what you do is you break the bond here. Well, oxygen gets 2 electrons, which makes a double bond. So double bonded pH3 that occurs there, and this makes this guy positive. Electrons here go here, which is 2 electrons. So 2, 4, 6, 8, 10. Overall, 10 arrows. Ew. Okay. Ready to answer some questions?
Yep.
Okay. I'm going to erase my arrows. Is that okay?
Yep.
Okay. Step 1 is an example of what type reaction?
Substitution?
Nope.
No.
I'm adding something. I'm adding
Okay, addition.
this guy. Yep. More specifically, it's a nucleophilic addition because I'm adding a nucleophile to the equation, right? Because it's giving up its electrons, making a nucleophile. So it's nucleophilic addition. Step 2, right here. Oops, that's the wrong one. Okay, step 2. I took an H,
Acid base.
acid base. Good job. Step 3. I replaced, it went from here onto the oxygen. And the nitrogen got a negative charge. So the negative charge and the pH3 swapped places. They did what? They were substitute each other. They swapped. Correct?
Yep.
Substitution. That is step 3. Step 4. H was added here, which is a acid base. If you're just moving a hydrogen, it's acid base. Step 5, I am replacing this with a negative charge, which is just substitution again. So there you go. That is topic 5. Does it make sense?
Yep.
Okay, there we go. Thank you guys for showing up. One person. Everyone else should feel bad. All you guys watching, feel bad. Okay.
All right. Thank you, Shane.
See you guys later.
Bye.
Or Athena, the only person here.
Bye.
Bye.